Good morning, everybody. Today we will continue with dielectrics. Actually, during the last lecture, I shortly talk about the dielectrics, application of dielectrics in capacitors. Today we will continue what is dielectric and how they affect the capacitance of capacitors. Here in the picture, you see metal conductor foil. This one, let me draw. This is conductor, metal foil. And here we have another conductor, this one. You can think about two parallel plates, okay, metal conductors. And with the green color, here you see an additional material. This is dielectric material. And you put this dielectric material between the metal plates, and then you completely fill this area with the dielectric material. Before the dielectric, this capacitor has certain capacitance, and after putting this dielectric material, the capacitance of the whole system changes, okay? We will learn today this property of the dielectrics. And a common type of capacitor uses long strips of metal foil for the plates, for the metal plates, for the conducting plates, separated by strips of plastic sheet such as mylar. So now let's learn how to increase capacitance of capacitors by using dielectrics. Here we have two metal plates. One has Q charge, the other one has negative Q charge, and there is a vacuum in between, nothing, okay? And by using electrometer, we measure the potential difference across the plates, and this electrometer measures this potential difference between two plates. It is V0. Okay, there is nothing between the plates, just vacuum we have. When we insert a dielectric material between the plates, this can be glass, this can be paraffin, or this can be polystyrene, or this can be mylar, okay? We just put here a dielectric material, uncharged dielectric material. And in the electrometer, we see that this V is reduced. At the beginning, the potential difference was V0 without dielectric material between the plates. But when we insert an uncharged dielectric material, we have another potential difference between the metal plates. Now we have V, and this V potential difference is smaller than the initial value. Remember the capacitance formula which we have learned during the last lecture. Capacitance is given with charge on the plate over the voltage difference between the plates, right? So Q charge does not change here. Q is same in case of with dielectric material, and without dielectric material we have the same Q charge, but the potential difference decreases after inserting dielectric material. If this potential difference decreases, then capacitance increases, okay? So as a result, if you insert a dielectric material between the plates of a capacitor, capacitance will be increased, okay? You will have much bigger capacitance compared to the initial capacitance without dielectric material. And let's see what is happening if we insert a dielectric material between the plates of a capacitor. In picture A, we have a plate It is positively charged and it has surface charge density sigma. And here on the right side, we have a negative plate. It has surface charge density of negative sigma. Okay, and then we have vacuum between the metal plates. And we have electric field lines from positive side to the negative side. And this electric field is given with E0. When we insert a dielectric material, which is shown here in picture B, what happens? The dielectric material is polarized and then induced charges occur. What is the meaning of this? I will explain later on, but here I would like to touch shortly. Remember the polarization which we have learned at the beginning of this semester. Polarization due to the electric fields. Remember this term from chapter 21, chapter 22. So when we insert a dielectric material between these two conducting plates, remember that here on the left side we have positive charges and on the right side we have negative charges. And due to polarization within the dielectric material, positive charges are collected here within the dielectric, don't forget, because they are attracted by these negative charges. You can consider like this. And negative charges within the dielectric material collected here on the positive side of the capacitor. Then you can consider that you induce charges within the dielectric material, and then we have induced charges. So we have positive charges here within the dielectric material, and we have negative charges here within the dielectric material. And you can consider that there will be an opposite electric field within the dielectric material. And the direction of this induced electric field is opposite to the initial electric field. At the beginning, we had this electric field, E0, and due to the induced charges, we have new electric fields within the dielectric, okay, due to induced charges. Then, in total, E0 from left to the right, and induced electric field from right to the left, and finally, the resultant electric field within this capacitor will be E, this one, from left to the right again. But what about the magnitude of this electric field? This electric field will be smaller than the initial electric field, okay? The electric field is reduced due to induced charges, because these induced charges produce also electric field in opposite direction compared to the E0. I hope this is clear. This is due to the polarization, and we have discussed the polarization in the previous lectures. Any question here? Then what about the relation between electric field when we have vacuum within the plates and the electric field when we have a dielectric material between the plates? This is the relation. The electric field when we have a dielectric material between the conducting plates is given with this expression. Initial electric field when we have vacuum within the plates over K. This is valid when the Q is constant. What is Q? The charge here, okay? Q is constant, charge of the capacitor. And the electric field is 0, can be written in this form. You know of this one from the first lectures. E is given with sigma over epsilon 0. This is the surface charge density sigma. Epsilon 0 is the constant, okay? And the final electric field, when we have dielectric material, it can be written in this form. Why? Look at the picture here on the right side. Let me magnify the picture. Look at the picture B. We have metal conducting plates and we have a dielectric material. And here on the left side in picture B, we have sigma surface charge density. And here we have, look at the picture, negative sigma I. This is the induced surface charge density, okay, induced within the dielectric material. And what about the total charge density here on the left side? Sigma minus sigma I. Then this term here, electric field after inserting dielectric material, can be written sigma minus sigma I over epsilon 0. Look at this area. Here we have sigma and here we have negative sigma I, and then surface charge density, total surface charge density can be written in this form. I hope this is clear. If not, please let me know. Okay, here we have this expression and we have also these expressions. Then I can write this expression. This is the induced surface charge density induced within the dielectric material. This is the surface charge density of the capacitor conducting plates, and we have K. K is the constant, dielectric constant. And what do you see here? If K is the property of this dielectric material, dielectric constant, and if this K is very large number, then what will happen? This sigma I will be nearly equal to the sigma. Then they cancel each other and the potential difference are much smaller than their values in vacuum. So what is the relation between electric constant and dielectric constant? It can be written like this. This is the epsilon. What is this epsilon? This is definition of permittivity, and it is also called as permittivity of the dielectric material, and it is given with K times epsilon 0. And finally, the electric field within the dielectric material. Remember the electric field here in this picture B. Here we have E, electric field, after inserting dielectric material. And this electric field after inserting dielectric material can be expressed in this form, sigma over epsilon. This is not epsilon 0, this is epsilon, okay? Finally, what about the capacitance? Just consider that the capacitance of this capacitor is C0 when we have vacuum between the plates. When we insert a dielectric material, then capacitance will be C like this. And what about the relation in between? We have this relation. This is the capacitance of a parallel plate capacitor after inserting dielectric material, C, and this is the dielectric constant of the dielectric material, and this is the capacitance of capacitor without dielectric. We have this relation, and remember the capacitance from the last lecture. Capacitance is given with this relation, or Q over V, okay? And just use this expression here. You know, this was the constant. This is the area of each plate. This is the distance between the plates, D. And here we have K times epsilon 0. K times epsilon 0 is the permittivity of the dielectric material. And then the final capacitance of the capacitor after inserting dielectric material, can be written in this form. Okay, so depending on the K here, we have epsilon 0 times K here, and depending on this K, this final capacitance of the capacitor increases. I hope this is clear. And with the same relation, you can also write the energy density in the capacitor after inserting dielectric material. It is written with this form. The electric energy density in a dielectric, which we have learned during the last lecture. This is energy per volume. It is given with 1/2 K epsilon 0 E squared. This is the magnitude of the electric field. What about the magnitude of the electric energy density? It is increased or decreased. Here we have K number, and usually dielectric materials have much bigger numbers compared to the dielectric constant of the vacuum. Let me explain like this. Here I have Q, negative Q, and I have nothing here, just vacuum. And then here I have certain electric field between the plates, and we have certain energy density U, okay, and vacuum has certain K value. This is 1, okay. And what happens if I insert a dielectric material between the plates? Again, we have same charges, and here we have the distance between the plates with a dielectric material, and now we have certain K of the dielectric material. And what is the electric field here? And what is the electric energy density? Electric field is decreased. We have already learned in the previous transparencies. And K is much bigger. K is increased. What about the U? Look at the U in this equation. Within the equation, we have K and electric field. K is increased after inserting dielectric, but electric field is increased. And if I take the square of E, then it will be decreased more. Then finally, this electric energy density in a dielectric will be smaller than this case when we have vacuum within the plates. I hope this part is clear. If not, please let me know. Any question? Okay, let me discuss some dielectric constants of different materials. Here we have vacuum. We have nothing between the plates. Let's consider. And the dielectric constant of the vacuum is 1. And just consider we have air within the plates. Just air, okay? And it is also close to the dielectric constant of the vacuum, 1.0059. And if you put here a Teflon between the plates, if you put a Teflon, it has dielectric constant 2.1. If you put Mylar, it has 3.1. If you put glass, depending on the type of the glass, it can have dielectric constant from 5 to 10. And if you put glycerin, for example, it goes up to 42.5, huge dielectric constant. And if you put water between the plates, dielectric constant is 80.4. And in technological applications, hafnium dioxide is mostly used material. Even with very small thicknesses, you can produce huge dielectric constant. As much as I remember, it is around 20, something like this. So this information about the dielectric constants of the materials, very important for technological applications, especially when you are designing capacitors. Let me show you here one application of capacitors. in the toolbox, here you see a guy and there is a wall here. And just consider that there are some metals within the wall, but you cannot see it, okay? There are metals, or there are some water pipelines or other pipelines within the wall, but you cannot see them, and you would like to use a drilling machine, and you would like to open a hole here. But before opening a hole, you would like to learn what you have within the wall, and you can check this one by using this tool. So what is this? Let me explain the application of this toolbox. Several practical devices rely on the way a capacitor responds to a change in dielectric constant. One example is an electric stud finder used to locate metal fasteners hidden behind a wall surface. It consists of a metal plate with associated circuitry. You can consider like this. Here you have a metal plate, okay? And just consider you have another metal plate here. And here you have a dielectric material, let's say, dielectric. The plate acts as half of a capacitor and the wall acts as the other half. If the stud finder moves over a metal fastener, the effective dielectric constant for the capacitor changes, which changes the capacitance and triggers a signal. This is the explanation, and let me also explain in this way. Just consider that you have two metal plates and you have nothing within the plates, and you have certain Q charge and negative Q charge here on the plates, and you have certain potential difference between the plates, and then you have certain capacitance. Okay? When you insert a dielectric material between the plates, this capacitance will be changed. If you insert another dielectric material with another dielectric constant, then you will have another capacitance. So depending on the dielectric material, you will have different capacitance between the plates if you have the same Q charge on the plates. So this instrument works based on this explanation, okay? So just consider that this wall has certain dielectric constant, but if there is a metal in this area, so then the dielectric constant will be different, okay? And if you have another material within the wall, if you have plastic, then the dielectric constant will change. Then this instrument will produce a signal. I hope this is clear. Okay, let me continue with example 24.10, a capacitor with and without dielectric. I have already discussed, you remember this picture. In the first case, we have vacuum within the plates, and in the second case, we have a dielectric material between the plates. And you know that the electric field between the plates will change after inserting dielectric material, and we will produce induced charges within the dielectric material. And what else? The capacitance will be C0 here, and here we will have another capacitance, okay? And here we will have epsilon 0, and here we will have epsilon, and here we will have K, okay? So everything changes if you insert a dielectric between the plates. Now we will apply all this information within this example. Suppose the parallel plates in this figure each have an area of 2000 square centimeter and are 1 centimeter apart. We connect the capacitor to a power supply and charge it to a potential difference to 3 kilovolt. Just consider here we have a battery and then 3 kilovolt potential difference is produced between the conducting plates and disconnect the power supply. We then insert a sheet of insulating plastic material. Dielectrics are insulating materials, okay? Don't forget. A sheet of insulating plastic material between the plates, completely filling the space between them. We find that the potential difference decreases to 1 kilovolt. So now, after inserting dielectric material, after inserting an insulating material, the potential difference is decreased to 1 kilovolt. At the beginning, it was 3 kilovolt. While the charge on each capacitor plate remains constant, Q charge does not change. Here we have sigma surface charge density, and here again we have sigma surface charge density. Find the original capacitance C0, magnitude of charge Q on each plate, the capacitance after the dielectric is inserted, the dielectric constant K of the dielectric material, the permittivity of the dielectric material, the magnitude of the induced charge Qi. Here we have induced surface charge density within the dielectric, and by using this one you can calculate this Qi on each face of the dielectric. The original electric field is 0 between the plates, and the electric field E after the dielectric is inserted. Many questions, okay? But all of them are very easy to calculate because you have already learned every required information to answer this question. Okay, let me start from the beginning. C0 is asked. So C0 capacitance, we know from the last lecture, is given with epsilon 0 times A over D, area of the plates. It is given in the question, this one, and epsilon 0 is constant, just put it there, and distance between the plates, it is also given. Then capacitance is given with 177 picofarad. And what about the charge on each plate? It is given with C0 times V0. Remember this formula. Nothing is new here. Capacitance is given with Q over V, okay? Just use this information. And C0 is initial capacitance, which we have calculated here. V0 is the initial voltage supplied from the battery. We know this one, 3 kilovolt, and put the numbers here. Then finally, you can calculate the Q charge on each plate, which is given with 0.531 microcoulomb. And what about the Q charge when the dielectric is inserted? The Q charge is unchanged, okay, because it is given in the question, but the potential difference decreased to 1 kilovolt. Then the capacitance after inserting dielectric material can be calculated with this formula, Q over V. Q is known, we have already calculated here, put it there. Voltage is 1 kilovolt, just put the value here. Then you can calculate the capacitance of the capacitor after inserting dielectric material between the plates. It is given with 531 picofarad. Look at the initial capacitance, C0, 177 picofarad, and final capacitance, 531 picofarad. So capacitance is increased. And by using this relation, K can be calculated. The dielectric constant of the dielectric material inserted between the plates. K is given with C over C0. Then it is calculated as 3. Okay. What was the K for the vacuum? For the vacuum, K is 1. Now we have K is 3. So K is increased. We have inserted dielectric. Then capacitance is also increased. Okay, K can also be calculated by using this relation, V0 over V. Don't forget this different types of calculation of K. They will be very useful for you during the exams. This is the initial potential difference between the plates, and this is the final potential difference. Then you can also find 3 here. And what about the permittivity of the dielectric material? It is given with K times epsilon 0. We have already learned this one. We have calculated K as 3, and epsilon 0 is constant. Then the permittivity of the dielectric material can be calculated like this. And what about the induced charge on the plates? Induced charge can be calculated by sigma I times I. How to get this relation? Remember the sigma. What was sigma? Sigma is surface charge density. It is given with Q over A, okay? Remember the lambda, linear charge density, Q over L. Remember the rho, volume charge density, Q over volume, okay? So just apply this formula here, and Q is required. Qi then can be calculated by using this relation. Okay, then if you use the formula here on the right side, then you can calculate Qi. This is the induced charge within the dielectric material. I have explained what is the induced charge, what is the induced charge density. And here we have Qi is equal to sigma I times A, and the Q is given with sigma times A. So we have this relation. How we have this relation? Let me go back. You see, induced surface charge density. Here we have sigma induced. Here we have sigma initial surface charge density. Here we have sigma, and here we have sigma I, you see. And we have this relation in between. This relation is given with 1 minus 1K. And remember the formula here. Sigma is given with Q over A, and sigma I is given with Qi over A, same area. So instead of sigma I, instead of sigma, just use this formula. Then you can get the same result for the Q value. Qi is equal to Q times 1 minus 1K. What is Qi? Induced charge within the dielectric material. This is the initial charge on the plates, and this is the dielectric constant of the dielectric material. And we know the initial charge. Where is it? We have calculated it. This one, 0.531 microcoulomb, and use it here. And K is calculated as 3. We have calculated K value here. And just put these numbers here, then we can calculate induced charge within the dielectric material. And another question, what is the initial electric field between the plates? Electric field is given with V over D. Initial potential difference is given with 3 kilovolt, and the distance is 1 centimeter. Then you can calculate electric field 3 times 10 to 5 volt per meter. And you can also calculate the electric field after inserting dielectric material. It is given with V over D. This is the final voltage between the plates, 1 kilovolt. Distance is same. Then you can calculate final electric field. What do you see here? Initial electric field E0 is 3 times bigger than the final electric field after inserting dielectric material. Why? Because we have K value, which is 3, okay? Or by using this equation, you can calculate final electric field. E is equal to sigma over E. This is the surface charge density, and this is the permittivity of the dielectric material. We have already calculated this permittivity of dielectric material. Where is it? Here. We have calculated permittivity of dielectric material. Just put the numbers here. Again, you can calculate 1 times 10 to 5 volt per meter. Here we have final electric field between the plates, and here again we have final electric field between the plates, but I have used different calculation methods, okay? But they give us the same result. Or you can calculate the final electric field by using this relation, final surface charge density over epsilon 0, okay? Then you can also get this number. Or you can also calculate electric field by using this formula, initial electric field over K, dielectric constant. Then again, you will get the 1 times 10 to 5 volt per meter. So how many methods? 1, 2, 3, 4 methods to calculate the final electric field. Okay. I hope it is clear. Let me continue with another example. Energy storage with and without a dielectric material. Find the energy stored in the electric field of the capacitor. In example 24.10, we are talking about this example. And the energy density both before and after the dielectric sheet is inserted. So initial energy stored in the capacitor is given with U0 here, this one, and it is written with 1/2 C0 V0 square. We have learned this one during the last lecture, and the initial capacitance of the capacitor is calculated, and initial potential difference is known. Then the energy stored in the capacitor when the dielectric is missing, so we have just vacuum between the plates, we can store this energy. And when we insert a dielectric material between the plates, then we can store this energy. Okay, so you can also check the answer by calculating this energy density. Okay, it is also possible. I will not go into detail. Okay, now we will continue with dielectric breakdown. Dielectrics are insulating materials. They are not conducting. They do not conduct the electricity. Okay, so just consider that here we have two metal plates, and this has Q charge. This has negative Q charge, let's say, and there is nothing in between. There is a gap, air, okay, or vacuum. So then there will be no conductivity between these two plates. We will have just electric field, okay, in this direction, from positive to negative. If here I use a dielectric material, now we have dielectric material. What about electrical conductivity between these positive and negative plates? Actually, there will be no conductivity because dielectrics are insulating materials. Let me change the color and then continue. So here I have inserted a dielectric material. Again, there will be no electrical conductivity. Okay? Because dielectric materials are insulating materials. They are not conductor. They do not conduct electricity. Okay? But if the electric field is strong enough, dielectric breakdown occurs and the dielectric becomes a conductor. So then you can conduct electricity from one plate to another plate. Let me change the color again. Then the electricity is conducted, let's say, okay, because this dielectric material becomes conductor. Now there is a conductivity within the dielectric material. When this happens, if the electric field is strong enough, the dielectric strength is the maximum electric field the material can withstand before breakdown occurs. So here we have electric field between the plates, and up to the maximum electric field, this dielectric material can withstand, okay, before breakdown occurs. But if you exceed this maximum electric field, then dielectric becomes a conductor. For example, here we have Pyrex glass, which has a dielectric constant of 4.7 and a dielectric strength of this value. This is the maximum electric field a Pyrex withstand before breakdown occurs. This is 10 to 7 volt per meter. But if the electric field is stronger than this value, then the Pyrex will conduct electricity. Okay. For example, dry air has a dielectric constant of this one, more or less around 1, like vacuum, and a dielectric strength 3 times 10 to 6 volt per meter. But sometimes the electric field here, this electric field becomes much stronger than this value, then the air becomes conductor, okay? Then you can see this lights, okay? Air conducts electricity if a dielectric breakdown occurs. I hope this is clear. Dielectric breakdown means that our dielectric material becomes a conductor and conducts electricity. But if the electric field is not strong enough, the dielectric materials are insulating materials and they do not conduct electricity. Let me show you here a bioapplication, dielectric cell membrane. In my previous lectures, I have shown you nerve cells. This is the inner part of the cell, and here we have a membrane. This is insulator, this part is insulator, and this is conductor, it is charged. And here outside of this insulating membrane, there is another conductor, okay? And this membrane here between two conductors is insulator. This red part is insulator, okay? Dielectric. Membrane is dielectric. And then there is a potential difference between two conductors, okay, with inner part and outer part. Here you see a three-dimensional representation of the membrane in a living cell. The membrane of a living cell behaves like a dielectric between the plates of a capacitor. The membrane is made of two sheets of lipid molecules with their water-insoluble ends in the middle and their water-soluble ends on the outer surfaces. Just consider that this is the membrane with yellow color, okay? And they are made from lipid molecules. And in this part, in the middle, they have water-insoluble ends, and in this part here in outer ends they have water-soluble ends. Conductive fluids on either side of the membrane, water with negative ions inside the cell and water with positive ions outside, act as charged capacitor plates. Just consider these parts are charged capacitor plates, and the non-conducting membrane, this part, this yellow part is dielectric insulator. It does not conduct the electricity, okay? the non-conducting membrane acts as a dielectric with K about 10. The potential difference across the membrane is about 0.07 volt and the membrane thickness is about 7 nanometer. So the electric field E volt per D in the membrane is about 27 volt per meter, close to the dielectric strength of the membrane. If the membrane were made of air, so now we have K is equal to 10. If this membrane were made of air, then K will be around 1. Then the electric field and the voltage difference will be by a factor of 10 and the dielectric breakdown will occur. Then this membrane will behave like a conductor if it will be air. Since it is made from lipid molecules, it has huge K dielectric constant, okay? Then it can behave as an insulator and there is no conductivity within this membrane. So it behaves like an insulating material. I hope this is clear. This is bioapplication. And let me discuss the molecular model of induced charge. Here in the previous part of my lecture, we have discussed these two pictures. Picture A, we have two metal plates, they are charged and we have certain electric field in between and we have a capacitor. And in picture B, we have inserted dielectric material between the plates, okay? And we have produced induced charges within the dielectric material and the electric field between the plates is decreased, voltage difference is decreased, okay? And we have now bigger capacitance of the capacitor after inserting dielectric material. We have discussed this one during the first part of this lecture. And now I will discuss why we have these induced charges, okay? Why we have these induced charges in the dielectric material. Actually, we have learned this one during the previous chapters when we were discussing the polarization, okay? The mechanism is based on the polarization. So let me explain. Some molecules such as water or nitrogen oxide form natural electric dipoles. What is the meaning of natural electric dipoles? Remember the water molecule. Here we have oxygen and we have two hydrogen molecules. They are positively charged and due to their positions in the water molecule, this side is positively charged, this side is negatively charged, and we have a polar molecule because we have electric dipole, right? Electric dipole, positive pole and negative pole. So this type of molecules are called as polar molecule, okay? When no electric field is present in a gas or liquid with polar molecules, the molecules are oriented randomly. Look at this picture A on the left side. Here we have a water molecule, positive side, negative side, another water molecule, let's say, okay, and there is no electric field. In the absence of an electric field, polar molecules orient randomly. But look at the picture B on the right side. Whenever we apply electric field, the polar molecules are oriented along the electric field. Okay, now what do you see here? Positive sides and negative sides are aligned along the electric field. So in an electric field, they tend to orient themselves as in this picture B I have explained. Okay, this is the polarization. And we have also discussed that even a molecule that is not ordinarily polar becomes a dipole when it is placed in an electric field. Remember this discussion which we have discussed again in the previous lectures. So here we have molecules. They are not polar molecule, okay? In the absence of electric field, non-polar molecules are not electric dipoles. Okay, you see neutral molecules here on the left side, but when we put them in an electric field causes molecules, positive and negative charges, to separate slightly. Okay, positive charges are located here and negative charges are collected here. Okay. In total, they are neutral. If you look from outside, they are neutral, but due to the electric field, we have collected negative ions, negative parts of the molecules in some part of the molecule, and other parts are located in another part. Then we have this type of alignment again. So this type of dipoles are called as induced dipoles. Okay, induced dipoles. So this is the mechanism occurs in the dielectrics. Here we have a positively charged plate in a capacitor. Here on the right side we have negatively charged plate, and we insert a dielectric material between the plates. Okay, actually dielectrics are insulating materials. Let's consider they look like this. They are neutral, but whenever we insert them in electric field in the capacitor, negative charges are induced on this positive side and positive charges are induced in this negative side. Okay, this is the mechanism of the induced charges in electric dipoles. I hope this is clear. Then we have this type of behavior. Here we have capacitor plate. This is positively charged, and on the right side another capacitor plate. This is negatively charged, and positive charges are aligned here at the negative side, and negative charges are located here close to the positive side. Okay, and all the molecules within the dielectric material are aligned like this due to the electric field here, okay, between the plates. Then we have the polarization of molecules within a dielectric material. I hope this is clear. This is actually comes from the polarization which we have discussed in the previous lectures. So now let's discuss this behavior in dielectrics in 4 steps. In picture A, we have no dielectric between the plates. We have just positive plate and negative plate, and there is an electric field in between, E is 0. This is the magnitude of electric field. When we insert a dielectric material, negative charges are collected on the left side of the dielectric material. Okay, look at picture C. And on the right side, we have positive charges. And due to this alignment of the charges within the dielectric material, we have another electric field within the dielectric material. Okay, we have electric field at the beginning here. We have shown in picture A, and in picture C, due to the polarization of the molecules within a dielectric material, we have an opposite electric field within the dielectric material, and the final electric field between the plates will be smaller than the initial electric field E0. Okay, this is the resultant field final electric field between the plates. We have already discussed this one in the first part of this lecture, but this nicely explains the decrease in the electric field between the plates after inserting the dielectric material, and also it explains how these induced charges are occurred within a dielectric material. Do you have any question here in this part? We have another example here related to the polarization. Actually, we have discussed this one, but I would like to repeat it here. Neutral sphere attracted to a charged sphere. Remember our experiment, you have a comb and you have charged this comb, and then here we have plastic or paper pieces, okay, many plastic, neutral plastic and paper pieces, and this is positively charged or negatively charged, okay, then this comb attracts this pieces, okay. So this was due to the polarization, and here again we have a positively charged sphere, okay, and here we have a neutral ball, neutral paper or neutral piece ball, okay, this is non-conducting and uncharged, and due to the electric field produced by this conducting sphere, this charged sphere, we have electric field, and this electric field aligns the charges within the non-conducting body, and then we have negative charges here and positive charges here, and between this A sphere and B sphere there is attractive and repulsive forces. Since negative charges are closer, then the net force will always an attractive force, okay, then this non-conducting uncharged body will be attracted by this A ball. This is due to the polarization. Okay, let me finish my lecture with this last information, Gauss law in dielectric materials. Here we have a picture on the right side. Let me show you what we have here. This is the positive side of the capacitor. This is the negative side of the capacitor. And here we have placed a dielectric material. Let me use another pen. Here we have a dielectric material. And within the dielectric material, negative charges are collected here on the left side and positive charges are collected here on the right side. Okay, now we are looking this side. Okay, we will investigate what is happening here. So this picture shows us this one. On the left side, we have conductor. And we have learned that within the conductor, electric field is zero. We have learned this information in the previous lectures. And here we have within a dielectric, we have electric field. Okay, these are the charges on the conducting plate. And this is the surface charge density sigma. And these are the negative charges collected on this side of the dielectric due to the electric field between the plates. Okay, and here I choose a Gaussian surface. You see, let me clean the board. Here I choose a Gaussian surface. What do you see here? We have the sigma surface charge density on the left side, and here we have negative sigma I charge density on the right side. We have positive charges here on the left side, and here we have negative charges on the right side. And then just apply the Gauss law here for this Gaussian surface. So you can also see this perspective view of this Gaussian surface. Okay, on the left side we have conducting plate of the capacitor, and on the right side we have some part of the dielectric material. And this is the Gaussian surface. Just apply the Gaussian surface. And now we have surface integral of Ke over a closed loop. Remember the Gauss law. It is given with E dA Q enclosed over epsilon 0, okay? And if you apply this one for this picture, then we have Ke times dA, Q enclosed free, total free charge enclosed by surface, and here we have electric constant. Okay, this is the Gauss law applied in dielectrics. Here we have an example. This is last transparency, a spherical capacitor with dielectric. This is example 24.12 in the book, but we have already discussed this example in example 24.3 in the last lecture. Use Gauss law to find the capacitance of the spherical capacitor if the volume between the shell is filled with an insulating oil with the dielectric constant K. So you remember these two concentric shells, which we have discussed during the last lecture. Here we have red color. We have a sphere with radius RA, and it has charge positive Q. And here we have with the blue color, we have an outer shell. It has radius RB, and it is charged with negative Q. And in the previous lecture, we have considered that between the shells, between the sphere, there is nothing, there is air or vacuum. But here we consider that between the spheres, we have oil, okay? Insulating oil or dielectric oil we have. Then what about the capacitance? We have two metal spheres, and what is the capacitor? In the previous case, in the previous lecture, since there is an air here, we have calculated capacitance according to the vacuum or air. But here, since we have oil, the capacitance will be increased. The capacitance will change, okay? Then we will have different capacitance if you put here oil or another dielectric material. Then just apply the Gauss law to find the electric field. This is the Gauss law for the dielectrics, which we have learned here. And here we have Ke times dA, and take this K and E out, and this is the area of the sphere if you choose a certain radius R, and this is the Q within this Gaussian surface. And then finally we have this electric field, Q over 4 pi K epsilon 0 R square. Here we have K epsilon 0. It is given with epsilon, permittivity of the dielectric material, okay? Then here we have electric field, okay? And what was C? C is given with Q over VAB. In order to calculate C, I need VAB. And we know that the electric field is given with 1 over K, right? You see? And voltage between the spheres will also be given with 1 over K, right? Then this capacitance, if you put here 1 over K, we will have this relation, K times Q and others, okay? Look at this result, 4 pi K here, okay? It comes here due to this relation in the potential difference between the spheres. So using the result, example 24.3, which we have done it during the last lecture, we find that capacitance with dielectric is given with this one. So the capacitance is increased by a factor of K. Okay, here we have K. I hope This is clear. Let me also read the evaluation part. If the dielectric fills the volume between the two conductors, the capacitance is just K times the value with no dielectric. The result is more complicated if the dielectric only partially fills this volume. This is important. Let me explain. We have one sphere, metal sphere, and we have another metal sphere. And at the beginning, there is vacuum or air between the spheres. And then we have certain capacitance. If you, let's say C0, if you fill this gap with the dielectric material with some certain K, then the capacitance of this system will be C, okay? And this C will be K times C0. This is the result. But in some problems, in some questions, maybe in exam, you can have a different situation. Only this part of the gap is filled with the dielectric material. Okay, and this part is air again, or this part, half of the gap is filled with dielectric with constant K1, and the other half of the gap is filled another dielectric material with dielectric constant of K2, okay? Then what about the final capacitance of the system? You can have this type of problems at the end of the chapter. Please try to solve all problems. Then it will be very helpful for you to get good grades in quizzes and also in midterm exam and final exam, and you will better understand the topic. So with this transparency, I finished my lecture. See you next week. Bye-bye.